Hello, everybody. Hey, this is a optional lecture and is designed for the people that have not taken calculus or are not in calculus right now for honors physics. Now, you guys, for the most part, there is not much calculus in this first quarter of um, physics, but the ideas behind it are really important and they're really not that hard. So I'm going to give you just a quick little lesson on calculus to give you an overview and the specific skills that you need to succeed in this class without having taken calculus already. All right, so now calculus is simply a part of math that actually makes a lot of more complicated situations a lot easier. And that is why it's so important. And it's broken into two different categories. And those two different categories are differential calculus and integral calculus. Now, there are other issues or other topics within calculus, but those are the two major ones. And in differential calculus, it's really all about calculating the slope of lines, which, remember, the slope of a line is a rate. So if we want to know the rate of change of something, for example, how much water people use, and then the cost per water, it might have a very complicated formula. If you're going to buy gas, the rate is $3 per gallon or $3.09 a gallon, something along those lines. That is a pretty straightforward thing, but if you buy 10 gallons times 3.09 is $30.90. Very straightforward. But if you have a more complicated series, for example, or equation, for example, if you're trying to buy water and the water company wants you to try to use the least amount of water, they might charge you with a more complicated formula in which it's not quite so simple to just say $10 times 3.09, okay? And those rates are slopes. So if we had an equation that looked like this, which is a cubic equation, a third order equation, it might look something like this. And we want to know what the rate is, let's say at 1, and then we wanted to know the rate, let's say at 2. Well, they're going to be different answers because if we look here, the slope where at 1 is going to look much different than the slope at 2. So that's really what differential calculus is all about, and we're going to talk more specifics about differential calculus. Now, the other part of calculus is integral calculus. And although it doesn't seem to be the same, there's just really the opposite mathematically to differential calculus. Now, one of the things that we've kind of been doing is calculating the area of a velocity versus time graph, which is going to give us distance. Okay, so for example, if you just had a car moving at 20 meters per second for a few seconds, and then it's going to decelerate. Well, the graph might look something like this. It's going at a constant velocity, and then it's going to slow down to nothing based on an acceleration. So we could calculate the area of this, and we can calculate the area of this because they are simple geometric shapes. So we could do the first one, length times width, and we could do the second one, and it would be 1/2 base times height, and we just add them together and get the overall distance. Well, if we had something that was more complicated, a more complicated curve, and we wanted to calculate the area under that curve, okay, then what we would do is we would approximate what the area is. And in order to help us approximate, we would kind of divide the shape underneath that curve into small little rectangles. And then we could just do length times the width of each of those rectangles and add them all together. Now, we're going to end up with some error there because because we could either overestimate or underestimate when we made our triangle, because it's not going to conform exactly to the shape of the line. Okay, so if we overestimate, then it's going to give us a certain error. If we underestimate, it's going to certain error. So the way we minimize that error is we make the width of each of those rectangles smaller and smaller and smaller. And remember, those rectangle widths are a determination of time. So we're going to take that integral, okay, and we're going to essentially do all those multiplications, and we're making the time smaller and smaller and smaller. So the time is going to go from something like delta t to little d, as in dt. So we'll talk more about that when we talk more about the differential, which deals with the slope. Okay, so now we can define the instantaneous velocity as the change in velocity over the change in time as t approaches zero. As t approaches zero. Now, really, this is just the slope on a position versus time graph. Okay. For example, if we had a position versus time graph here, and we looked at this slope right there, and we wanted, hey, what is that slope? We would do the rise over the run, okay? And that's going to be 4 divided by 2. So our velocity, 4 divided by 2, would equal to 2. Okay, well, if we wanted to make that time smaller, then we could say 2 over 1. So your rise is 1 and your run is 2. So we'd say 2 divided by 1, and would give us a value of 2 meters per second. And if we wanted to get smaller, we could go a half, and that would be 1 divided by half, which would be 2. We could do 1/4 or 1/2 divided by 1/4, and that would still equal 2. And all of those cases, we are calculating the slope. And the reason, as you can see, is that since that is a straight diagonal line, it doesn't matter between what 2 points that we use, it's still going to give us a slope of 2. Now, if we move on to an equation like this, okay, or a line that is represented by this equation, then we can see here, using our sloperometer, okay, that our slopes are going to change depending on where we are. Okay, so in order to illustrate that, we're going to start here, let's say at t equals 3 seconds, right? And if we look example here, t equals 4 seconds, and we wanted to calculate the slope between those two lines, okay, then we would say our final, which is 4 minus 3, would be 1. Okay, but the rise there is not so apparent. Okay, in order to make this a little more obvious, I'm going to take this section right here, and I'm going to kind of blow it up to make it more of an exaggerated curve. So now we're down here at t is equal to 3, and up here we'll have t is equal to 4. So if we wanted to calculate the slope here, okay, so again, obviously our run here is going to be delta t, which is going to be 4 minus 3. Okay, so we can go delta x divided by delta t, and on the bottom is the easy one, 4 minus 3, which is equal to 1. Now, on the top, it's a little more complicated. So if we put in 3, for t, we're going to get 3 squared, which is 9, minus 4 times 3, which is minus 12, plus 5, and that is going to give us 2, right? Now, that was our initial position. Now, our final position is going to be 4. So 4 squared is 16, minus 4 times 4 is minus 16, plus 5, and then that would give us 5. So now our change in x is 5 minus 2, which is 3, divided by our already 4 minus 3. So our rate there, which would be 3. The slope is 3. And because this is time and position, we're going to get meters per second. Okay. Now, what if we change this and instead of having 4, we use 3.25? Okay, so we can see here that when we connect those two lines, okay, and those are chords, then we can see that the slope is less. And if we make this smaller, like 3.1, okay, then that is going to be even smaller. And if we use 3.01, then that is going to be even smaller. So what I've done here on this next page is I've done these calculations, okay? So in the first case, we did the change in time was 4 minus 3, which was 1. 5 minus 2 was 3. 3 divided by 1, so our slope was 3. Now if we use 3.25 minus 3, okay, obviously our change is 0.25. Now we got to plug those numbers into this equation here, and we're going to end up with 3.25 minus 2. Now the 2 is the same thing as when we plugged in for 3 seconds. If we do 3.1 minus 3, that's 0.1, and we plug those numbers in, we get 2.21 minus 2, that's 0.21, and 0.0201. And when we do the slopes of all those, 1.25 divided by 5, 0.21 divided by 0.1, 0.0201 divided by 0.01. And what's happening here is that slope, as we already pointed out, it's getting shallower, 3, 2.5, 2.1, 2.01. They're getting smaller and smaller. But as we make this t approach 0, okay, and this is known as the limit, okay, as t approaches 0. So if we made this point 0.00001, what number is it coming close to? And we can see here through this trend, it is approaching 2. Okay, so that means once we got down here to a point where the difference in the times is so small, okay, we would end up with a tangent. So instead of being the distance between 2 points, we make the t so small, it's getting closer and closer to only one number, okay, which would be, in this case, 3 seconds, okay? And at that point, our slope would end up being equal to 2, okay? So that is the theory behind a differential, is we make the time get smaller and smaller and smaller, okay? So now, instead of saying our velocity is equal to delta x over delta t, now we're going to make this t super, super small, which is called dt. And that's the t as the time gets closer and closer to 0. Okay, and then this would be dx. So our velocity is equal to dx dt. Now, what we're going to do now is to show you the easy way to determine what the slope is at any given point with a polynomial. Okay, with a polynomial. So we are going to take this original equation and we're going to say x is equal to t squared minus 4t plus 5. And if we go dx dt, okay, then the rule is we're going to take the variable, which is t, and we're going to look at its exponent. Okay, so we're going to say rather dx dt down here. So we're going to take this exponent of this variable, okay, and we're going to bring it down. And when we bring it down, it's going to be 2 times, okay, this variable minus 1. So we're going to say 2 minus 1, and that is going to give us 1. And then we're going to take, now this exponent of this t is 1. So now we're going to say 1 times negative 4 is negative 4. And now we're going to say t1 minus 1 is 0. And t to the 0, as you know, is equal to 1. 4 times 1 is just equal to 4. Now, when we don't have a variable, so for example, we're going to have t to the 0, 2, 1, 0. And now we're going to take 0 times 5, which is going to be 0 times t to the negative 1. But since we're multiplying by 0, it doesn't matter, okay? So essentially, this right here is equal to the equation for the slope of the line. And remember that this is v is equal to dx dt, because dx dt is equal to our velocity. So now let's plug in 3 like we did in our example right there. And we can say 2 times 3 minus 4, 6 minus 2, that gives us a slope of 2, okay? Which is what we figured out by going through all of this stuff right here. That is the essence, because that is the essence of differential calculus for a polynomial. Okay, now there are other components where we would take differentials, but that is really all we have to worry about when it comes to this class. And I just want to show you one more thing here. And let's say we had a more complicated question. Let's say we had x is equal to 3t cubed minus 2t squared plus 5t minus 6. So if you had that and you wanted, and I asked you for the equation for velocity, if this is the equation for position. So what we would do is we would take the differential of this, okay? Now remember, that's equal to velocity. So now we're going to apply our rule, okay? We're going to say the exponent times 3, which would be 9t. Now we're going to say 3 minus 1, which would equal to 2. Now we're going to say 2 times negative 2 is negative 4. T, 2 minus 1 is just 1, okay? Plus t to the first is t. 1 times 5 is 5 times t to the 1 minus 1, which is 0. T to the, anything to the 0 is 1, so 1 times 5 is just 5. This is t to the 0. 0 times 6 is just 0, so that part doesn't matter. So this becomes our equation. That becomes our equation for velocity. Now, you may remember from our discussions, acceleration is the change in velocity over the change in time. So if we were to take the differential of this velocity equation, we're going to get the acceleration for, we're going to get the equation for acceleration. All right, so this would be dx squared over the second position, which is equal to the change in velocity over the change in time, which is equal to acceleration. Okay, you guys, all this complicated stuff is just telling you, it's just the way that it's stated. So don't stress out about that. You don't have to worry about this, but as you see it more and more, it'll become more familiar. So now we're going to take the differential of this. So that would be 9, or 2 times 9, which would be 18 t to the 2 minus 1 is just 1. So that's 18t minus, remember there's a 1 there. So 1 times 4 is 4. T minus t to the 1 minus 1 is 0, so that's just going to be 4. And then as we talked about here, t to the 0, that doesn't matter. So our equation for acceleration would be that. So when you have a differential of a polynomial, then calculating or coming up with the equation for velocity and the equation for acceleration just becomes the successive differentials, which is, with just a little bit of practice, pretty easy. And now, if we wanted to know the speed at any particular time, okay, if this was our equation, we could put in, for example, 1. What is the speed at 1 second? And we would say 1 squared is 1 times 9. So we'd have 9 minus 4 plus 5. 9 minus 4 plus 5. And our velocity at 1 second would be 10. Okay, well, what would our acceleration be at 1 second? And now we could say 18 times 1 is 18 minus 4, and our acceleration would be equal to a 4. And obviously, because it's more complicated, if we change the time, then we're going to change our value because it's going to change over time. So, you guys, that's it. We'll practice. I'll give you guys help, but that's essentially what you need to know for this beginning part of physics with regards to calculus. Okay? Take care.